last lecture for electromagnetic fields theory, which is lecture 8 on time-varying fields and Maxwell's equation. The second part. These were the Maxwell's equation that we discussed in the previous class. So just a recap: the differential form, the integral form, the differential forms here, the integral form, the first one being Faraday's law, second one being Ampere's circuital law, the third one being Gauss' law, and the third one saying no isolated magnetic charge exists. Now the next thing we'll do is to discuss the boundary conditions. And in discussing the boundary conditions, we'll use the integral form of this equation. So keep them in mind. For example, we'll start with the integral form of the divergence of d equals rho v, which is integral d ds equals integral rho v dv. So that's what we have here. And if you look at this diagram, which is a cylindrical shape, so part of the cylinder is in medium 1, the other part is in medium 2. So the line here is a boundary between two medium. That's the boundary between two medium. Now the surface area here is delta S. Similarly, the surface area here is also what? Delta S. So if we are looking for the summation integral d ds, that is the summation of the electric flux density with respect to the surface, then in medium 2 here, we have dN2. And the surface ds in medium 2 is just simply delta S. And then in medium 1, now you can see the direction of the normal. While this is into the boundary, this is out of the boundary. So they are like opposite of each other. So we have minus dN1 in medium 1, also delta S. And that should be equal to rho S, which is a charge here. The surface charge times the surface delta S. So you can see that delta S cancels out because it's common to all the terms. And therefore we have D2N minus D1N equals rho S. Or you can write it in this form. I don't know why the bracket always doesn't show. So because we're talking about the normal component of D, so it is N, which is the normal to the surface. This N here, normal to the surface. Then times D2 will give you D2N. N times D1 will give you what? D1N. So N dot D2 minus D1 equals rho S. So what it means is that for the electric flux density, it is not continuous. Not continuous across the interface, because they are not the same in medium 1 and medium 2. If they were the same in the 2 medium, then the difference will be what? 0. But because they are not the same, the difference is not 0. Okay? Now, so the difference is equal to what? Rho S, which is the surface charge density on the surface or at the interface between the medium. So we say the electric flux density is not continuous across the interface. And the amount of discontinuity is equal to what? Rho S, which is the surface charge density at the interface. We have done this for static electric field. We have done this for static magnetic field. We are not doing it for a dynamic field, which is an electromagnetic field. Then we can do the same thing for B. From the divergence of B equals 0, we come up with the volume integral of B dV equals 0, and then use divergence theorem to convert this volume integral to a surface integral. So you have integral S B ds equals 0. That's this equation here. And now we can use that again for the same pillbox shape that we have part in medium 1 and part in medium 2. And then we can see that it will be the same thing as the normal component of the flux density, except that in this case it is equal to what? 0. So as for the normal component of the flux density, it is continuous across the interface, because then B2n equals B1n. And therefore we can write B2n will be what? N dot B2, and then B1n will be N dot B1. And those are the normal components of the magnetic flux density. That one is continuous across the interface. Now to look at the what you call it, the tangential component. So this is the interface between the two mediums. So this is medium 1, here medium 1, and this one is medium 2. Okay, medium 1, medium 2. And they are distinguished by the colors. So we are looking at a region between medium 1 and medium 2 defined by this rectangle here. Now what you can see is that the rectangle has a height of h. We are assuming that this h approaches what? 0. It means that the width is very small. In other words, whatever we are considering then, we are considering at the boundary, not in the other medium. So the width or the height h here is approximately equals 0. And from the curl equation, curl of E equals minus del B del T, we get this equation when we integrate. That's the integral form, because we'll do the surface integral and then convert that to a line integral, and then we get integral E dl will be equal to minus integral del B del T del S. So now as the height h approaches 0, if this height is approaching 0, then we don't have a surface, we just have a line.
Oh, follow it, follow it.
Okay, so if this height here is 0, so it means that it's almost becoming what? A line. Almost as though this one is merging with this one. So that's almost becoming a line. In that case, the surface integral of B, which is integral del B ds del T, because we don't have a surface, we just have a line, then the surface integral will vanish. It will approach 0. In that case, if we are summing E dl around this rectangle, then in medium 1 here, the E here with the tangential component, E1 tangential. The L will be this, actually is delta L here. So times delta L. And as we can see, where medium 1 is in this direction, in medium 2 is what? In this direction. So it will be minus E2 tangential delta L, and that should be equal to 0 because this one vanishes. So we have this equals 0. Obviously, delta L cancels out, and then you have E1 tangential equals E2 tangential. In other words, the tangential component of the electric field intensity is continuous across the interface. E1 will be equal to E2 across the interface. The tangential component of the electric field intensity is continuous across the interface. Now we come to the magnetic field intensity. And just as we did for the electric field intensity, for the magnetic field intensity also, starting from curl of H equals what? J plus del D, del T. We can do the integral to arrive at this one, because we'll begin with surface integral, and that surface integral will be converted to a line integral. And then we have this. And just as we made the argument for del B, del T ds, the integral of that approaching 0, because the height h is approaching 0, and therefore the surface integral of B vanishes. The same thing here, the surface integral of what? D here will vanish. And therefore this, the sum of H delta L, just as we did for E, will be delta L times H2T minus delta L times H1T. Remember the direction. Okay, so this is the boundary 2, boundary 1, where H1 will be in this direction and H2 will be in this direction. And the length here is what? Simply delta L. So if you want to sum across this height, H is approaching 0. So it's as though these two lines are merging at the interface. So if you want to sum around this rectangle, it is H1, which on the surface is a tangential component. Okay? Sorry, this is medium 1, H1 here, and then H2. We have H2 tangential times the L, because this is HDL. And then you have delta L here, and then minus, because of the opposite direction, H2 tangential, H1 tangential, delta L, that is equal to what? Sorry. That is equal to delta L times what? J. And this J is a surface charge, but then with respect to the line delta L. So this way we have delta L cancels out, and H2T minus H1T will be equal to what? J here. And the tangential component is what? The cross component. The normal component is N dot, whatever, B or D, N dot B or D. But the tangential component is cross, so N cross E or N cross what? H. So then we have N cross H2 minus H1 equals what? JS. So it means also the tangential component of the magnetic field intensity is not continuous across the interface. And the amount of discontinuity is equal to the what? Surface current density, which is a JS. So this treatment is very similar to the treatment we've had for the static electric field and for the static magnetic field. Now, because we said earlier that E1 tangential equals E2 tangential, and remembering the relationship between E and D, D equals what? Epsilon E. So it means that E must be equal to what? D divided by epsilon. So we can write that D1 tangential over, so what will happen is that you have D1 tangential divided by epsilon 1 will be equal to what? D2 tangential divided by epsilon 2. Or you can bring D2 down here, and then you have D1 tangential over D2 tangential will be equal to epsilon 1 divided by epsilon 2. And that's the results that we have here. So similarly, we are not dealing with a case where rho S equals 0. So at an interface between two lossless dielectric material, there are usually no free charges and no surface current density. So the initial discussion yielded, N D2 minus D1 equal what? N dot D2 minus D1 equals what? Rho S. But rho S is 0. And if rho S is 0, then this one means that D2 minus D1 will be equal to 0. And for the tangential components of E, in E1 tangential will then be equal to E2 tangential, and you can express that in terms of what? The electric flux density. Similarly, for the H, it is H1 tangential, H2 tangential minus H1 tangential is called J. But since there are no surface current density, then H1 tangential must be equal to H2 tangential. It was H2 tangential minus H1 tangential equals what? Js. But if there is no Js equals 0, then H1 must be equal to H2 tangential. And then if you remember the relationship between H and B equals what? Mu H. Or H must be equal to what? B over mu. So you can say B1T over B2T, just as we did for this one, equals mu1 divided by mu2. And then for the normal components, because rho s is 0, as I indicated, from n d2 minus d1 equal rho s. Since rho s is 0, d1 normal, the normal component of d1 will be equal to the normal component of d2. And since d is epsilon E1, this will also be the case for the electric field intensity normal to the surface. And again, already we knew that integral B ds equals 0 from divergence of B equals 0. So this is already the case. B1n will be equal to what? B2n. And therefore mu1 H1n should be equal to mu2 H2n. Now, if we keep this in mind, we can evaluate the case at the interface of a perfect conductor. Remember what discussion we had about the perfect conductor. So at the interface of a perfect conductor, in the interior of the conductor, E equals 0. And I hope you remember that discussion from static electric field. The E is 0 in the interior of the conductor. So from this equation here, integral C integral C E dl equals minus integral S del B del T ds. From this equation, since E is 0 in the interior, this is 0, then B also becomes what? Equals 0. And then from D equals epsilon E, E is 0, therefore D is also 0. So D here is also 0. And from H equals B over mu, since B equals what? Mu H, then H equals B over mu. Then since B is 0, then H must also be what? 0. So in other words, in medium 2, all the parameters are equal to 0. E2 equals 0, B2 equals 0, H2 equals 0, and D2, they are all equal to 0 in medium 2. So the fields exist in medium 1. So the tangential components then become, since from the previous discussion, E1 tangential equals E2 tangential. If in medium 2, E2 equals 0, then E1 must also be equal to what? 0. So E1 tangential equals 0, E2 equals 0. And then, since H2 is 0, from N cross H2 minus H1 equals 0, then if H2 is 0, then H1 must also be what? Sorry, this is equal to Js. Yeah, if you remember, this is equal to Js. So if H2 is 0, then N cross H1 is the H1 tangential. That one must be equal to what? Js. That's what we have here. So that one in H1 tangential or N cross H1 is equal to Js. And then from N dot D2 minus D1 equal rho S, because it's a perfect conductor, so the current density exists at the surface of a perfect conductor, and the surface charge density also exists. Again, if D2 equals 0, then D1 normal must be equal to what? Rho S. And finally, as for B, we know B1N equals what? B2N. Therefore, if B2 equals 0, then B1N must also be equal to what? 0. So, at the interface of a perfect conductor, only the tangential component in medium 1 and the normal component in medium 1 exist. All the other fields are 0. Okay, so now this is where we begin to have a feel of electromagnetic field theory from this point going on. I told you that the electric field intensity and the magnetic field intensity, they are all a function of x, y, z, and t. That's in rectangular coordinates. In rectangular coordinate, they're a function of x, y, z, and they also vary with time. So there are 4 parameters to every one of those field parameters. So there are 4 variables, sorry, to every one of those field parameters. So whether it is the electric field intensity, the magnetic field intensity, and the what do you call it? Magnetic flux density. They all have, they vary as a result of, they vary in the direction of x, y, and z, and they are also a function of t. Now the variation with respect to t, we can represent by what? Ej omega t. Remember what Ej omega t is? Ej omega t is actually cos omega t minus j sine what? Or plus j sine what? Omega t. So if we take the real part of this equation, which one is the real part? Cos omega t. That means that we are dealing with only a cos omega t function. If you remember from applied electricity, we'll start with a function, a sinusoid, which is either what? Sine omega t or what? Cos omega t. But in this case, we are looking at the real part, which is what? Cos omega t. And that is why the t component is expressed as Ej omega t, but not all of it. Only the real part of Ej omega t, which is what? Cos omega t. So this will represent E and this will represent what? H. Now let's see what information we can derive from that. So when you have Ej omega t, so E is a function of, E has the component of what? Ej omega t. If you differentiate this one with respect to time, if you differentiate E to j omega t, you get what? J omega. Then times the whole thing again. And the whole thing will be what? E, which is a function of x, y, z, and t again. So if you differentiate E, you get j omega E. If you differentiate, if you integrate E, then you get E over j omega. Similarly, if you differentiate H, you get j omega H. If you differentiate, if you integrate, you get H divided by what? J omega. And so we'll use this in finding some equations for the Maxwell's equation. If you remember, curl of E was equal to what? Minus del B del T. So by what we just discussed, if we differentiate B, which varies sinusoidally, then curl of E will be equal to what? Minus j omega B. And we know from the constitutive relations, B equals what? Mu H. Therefore, curl of E must be equal to what? Minus j omega mu H. If you substitute B by mu H. And that is what you have here. Similarly, curl of H, curl of H was equal to what? J plus del D del T. If you consider the situation where we're dealing with what? Source-free field, it means J is 0. There's no source, no current density. Then it means curl of H must be equal to del D del T. And del D del T will be equal to what? J omega D. Again, but D equals what? Epsilon E. So you have J omega epsilon E. And this J omega epsilon E is what you have here, J omega epsilon E. So these are the time harmonic version of the Maxwell's equation, the curl equation, the two curl equation. So curl of E equals minus J omega mu H, and curl of H equals J omega epsilon E. Now, if we take a second curl of E, if we take a second curl of this one, we take the curl of that one again. So we have curl of E. So curl of E must be equal to what? Minus J omega mu and then curl of H, because we are taking a second curl of that equation. But we already have an equation for curl of H here. So we can substitute it here. So the curl of E will be equal to minus J omega mu, and curl of H is what? J omega epsilon E. So you have J squared, and J squared is minus 1. So the J times J is minus 1. It cancels out this minus. And then you have omega being squared. And then you have mu. And then you have epsilon. And then you have E. So that is curl of E. Curl of E equals omega squared mu epsilon E. Now this is going to yield the very important information, as you see in the next slide. So this is what we saw. Curl of E equals omega squared mu epsilon E. But this curl of E, there's an identity for it. The identity is that you can write curl of E as the gradient of the divergence of E. That is del into bracket del dot E. This del is gradient, and this del dot E is the divergence of E, minus del squared E. This is an identity like you have for trigonometries. When you say, for example, cos squared theta plus sine squared theta equal 1. That's an identity. So similarly, for the curl equation, this is an identity. Now, we are talking about a source-free field. If it is a source-free field, then we know that the divergence of D equals rho S, right? Now, if you represent D by E, then you have divergence of what? Epsilon E equals rho S, or the divergence of E equals what? Rho S over epsilon. So if we're talking about a source-free field, the rho S is equal to what? 0. That means the divergence of E must be equal to 0. So this component here, which is the gradient of the divergence of E, or this component here, is going to go to what? 0. So then we have minus del squared E equals what? Omega squared epsilon E times E. And that is the equation that we see in the next slide. So noting that del E equals 0, sorry, divergence of E equals 0, then this component here will be 0. So we are left with this component. So minus del squared E equals omega squared mu epsilon E. And actually del, if you remember, del is given by what? In the AX direction, del X plus AY, del Y plus AZ, del Z. That's what del is. And for del squared, For del squared, then it is del squared del x squared in the x direction plus del squared, whatever the, so here in this case is e. Del squared e del y squared plus del squared e del z squared. So this will all be equal to what? Omega squared mu epsilon times what? E. And so you can write that since this is negative here, you can rewrite it as what? You can write it as del squared, that is, take this one across, del squared e plus omega squared mu e mu epsilon times e equals 0. And now we can derive a similar equation for the h component. So we have these two equations. These two equations are called the wave equation. And very soon you see why they are called the wave equations. So what we had was del squared e plus omega squared mu epsilon e equals what? 0. So, and then for the h is del squared h plus omega squared mu epsilon h equals 0. So the component here, omega squared mu epsilon, we shall substitute as what? K squared. And therefore K will be equal to square root of omega squared mu epsilon, which is given by what? Omega into bracket mu epsilon. This K is called wave number. Wave number or propagation constant. So wave number or propagation constant. And again, these equations are called the wave equation. Another name for them is what? The Helmholtz equation. The Helmholtz equation. And these two equations underline wave propagation, as we shall see very shortly. So if we consider only the x component, which is propagating in the z direction, then instead of del squared e xyz del x squared plus del squared e del y squared plus del squared e del z squared, and this e will be a function of what? xyz. We are considering only the x component, which is traveling in the z direction. So that will be del squared ex del z squared plus k squared ex equals 0 for simplicity. Now you can see that this is a second order differential equation. And we know how to write the solution for a second order differential equation. You need a constant, and that constant we're using E plus. That's the first constant. And the second constant we're using what? E minus. And then of course E to the power what? J, K times Z, which is the direction of propagation. So we have E minus JKZ and then E plus JKZ. So that is the solution for this Helmholtz equation in X. So now what information can we get from this? Now we can write this in terms of the sinusoidal function. Remember I said, so here E, J, K, Z will be what? Cos omega t minus K Z, and then for the positive one also we have cos omega t plus kz. Remember what I said about taking only the real parts? Ordinarily, e to the jx is what? Cos x plus j sine x. But I said that we are considering only the real part. And the real part of this is the cos x part. So if we write this in sinusoidal function, then it will be, my distance is jump up. So the real part is e of this. Then we are going to have e cos omega t minus kz, and this e plus, then plus e minus the two constant cos omega t plus kz. So what it means is that we have two waves. One is propagating in the positive direction and the other one is propagating in the negative direction. And then this, what is in the bracket here, omega t minus kz, is the phase with which the wave is propagating. Let me rewrite them here. E plus, E plus cos omega t minus kz plus E minus cos omega t plus kz. So two waves, one is propagating in the plus z direction, the other one is propagating in the minus z direction. Now what is in the bracket is the phase, because you always have what? Cos phi or cos theta. So what is in the bracket is the phase. This one is the phase. So if we assume that the phase is constant, then omega t minus kz must be equal to what? A constant. If we make z the subject, then z will be equal to what? Omega t minus constant all divided by k. If we differentiate z with respect to t, then we have the z dt will be equal to omega, because we're differentiating with respect to t. Omega, if we differentiate a constant, is 0. So omega divided by k. Now this omega divided by k is very important, because if you remember, k, we gave k as what? Equal to omega square root of what? Epsilon e. That was the value of k. Therefore, if you substitute omega square root of epsilon e, omega will cancel out, and then you get, so k is this. Or the z dt will be equal to what? Omega divided by, what is k? K is omega square root of what? Epsilon e. So omega cancels out, and this is 1 over square root of epsilon mu, or mu epsilon. Now, if you differentiate distance, z is distance. If you differentiate with respect to time, then you get what? Velocity. And since omega t minus omega t minus kz is the phase, when you differentiate this distance with respect to t, you get the phase velocity. And that phase velocity is given by 1 over mu epsilon. So in free space, we know what the value of mu naught is, and we know what the value of epsilon naught is. In free space, Vp, if you evaluate, will be equal to what? 3 times 10 to the power 8 meters per second. That is, if you evaluate this for free space by substituting mu naught, epsilon naught, this will be approximately equal to 3 times 10 to the power 8 meters per second. So it was from this that scientists came to understand that there exists electromagnetic waves which can propagate with the speed of light, which is given by 3 times 10 to the power 8 meters per second. Now the idea that Vp, the phase velocity, is the same thing as the speed of light c, means that we can actually create the wave and allow it to travel with the speed of light. And then we can put some information on the wave so it can carry it from one point to the other. And that was the birth of radio communication or wireless communication. That's how wireless communication was birthed. Because VP, which is 1 over mu epsilon naught, 1 over square root of what? Mu naught epsilon naught. This is equal to what? C, the speed of light. And so it was identified that the light itself was a part of an electromagnetic wave spectrum. And that light is part of that spectrum. And they all travel with the speed of light, c. And that was the birth of, I said, wireless communication or radio communication. So we are also familiar with something called wavelength. Again, this is not very visible, but the phase was what? Omega t minus kz. If this should advance one wavelength, then you would have minus, again, omega t minus, sorry. You have omega t, the phase was omega t minus kz. If you should advance one wavelength, then it will be minus, again, omega t minus k into bracket z plus lambda, where lambda is the wavelength. Let me just write it in a place where it can all come in full. So omega t minus kz, advance one wavelength, it will be minus omega t minus k into bracket z plus lambda, where lambda is the wavelength. And the difference here should be equal to what? 2 pi. Because that's the full phase from one point to the next point of the start of the wave again. It's 2 pi. If you work this out, this omega t minus this omega t, so they'll cancel. Minus kz here will cancel this kz. So you're left with what? Minus kz here, and this minus kz. So this minus kz plus kz, they'll cancel out. So then you have k lambda will be equal to what? 2 pi, or lambda equals 2 pi divided by k. So we have this equation here, which is lambda, my thing is all messed up. Lambda equals 2 pi divided by k. And then we remember that we said the Vp equals what? Omega over k from the previous slide. Vp equals omega over k. And then lambda also equals what? Two pi over k. Vp equals omega over k. Lambda equals 2 pi divided by what? K. So from this one here, we can say that k is equal to what? Omega divided by Vp. And put k here in place of omega over Vp, then you have lambda must be equal to what? 2 pi divided by omega divided by what? Vp. Or this is the same thing as Vp up times 2 pi all divided by what? Omega. And remember, omega is what? Omega equals 2 pi f. Omega is 2 pi f. So if you put 2 pi f here, then you're going to have lambda will be equal to what? Vp times 2 pi divided by 2 pi f. 2 pi cancels out, and you have Vp divided by what? F, or your famous equation Vp equals what? F lambda, which is the equation for the speed of an electromagnetic wave. Vp equals what? F lambda. And that Vp we say is what? C, or the speed of propagation of light. Now, similarly, you can look at that same case for what? H, which is the magnetic field intensity, because curl of E equals minus del B del T. So if you use the time harmonic form, then we have curl of E equals what? Minus J omega B. But we know B equals what? Mu H. Therefore, curl of E must be equal to minus J omega mu H. Therefore, H from this is equal to what? Curl of E divided by negative J omega mu. So if we can find the curl of E, then we can find H. Now, because we have an expression for E, we have found a solution for E. What is the solution for E? This is a solution for E here. So we can do the curl of this EX here, and then when we divide by J omega mu, then we'll find what? H. And sorry, we didn't do the vectors, but if you want the curl actually, I showed you what del of a vector is. The curl of a vector, let's say curl of E. I'm sure you did this in mathematics. Is AX, AY, AZ, del X, del Y, del Z, and then EX, EY, EZ. So you take this determinant. Fortunately, we are only looking at the variation of what? Variation in Z only. So it means this one will be 0, this one will be 0. And the X component also, we are looking at only EX, so EZ and EY is 0. So if you do the curl, you take the determinant, you realize that only EX and delta Z will be in the equation. And if you differentiate EX with respect to Z, differentiate EX with respect to Z, this will be what? Minus JK. Minus JK, again, times what? E plus, then E minus JKZ. Then this will be plus. Again, if you differentiate this, it will be what? JK, then E minus EJKZ. And all of this we are dividing by what? J, negative J omega mu. So if you do that, we can actually factor out K. K is common. J cancels out. The negative cancels out. So this one here will be negative, right? This plus will become negative because we have negative here. J cancels out. And then we have omega mu. And we can factor out K. If we do that, we're going to have K, that's this K. We're factoring that out. Divided by omega mu. Then into brackets, you have E plus E minus JKZ. And this will be minus, because this minus will affect this one. And then we have what? E minus, then E, J, KZ. So that's what you have. So what is K divided by omega mu? Remember that K itself equals omega square root of what? Epsilon mu. So what is K divided by omega mu? That will be omega square root of epsilon mu over what? Omega mu. So omega cancels out, and this raised to the power half, this is 1, so this becomes minus, and this will be square root. Let me continue here, please. This will be what? Square root of mu, sorry, square root of what? Epsilon, divided by what? Mu. And this is called what? The it's called the impedance, or the wave impedance. And that equation is what you have in this slide here. Sorry. Equals square roots of what? Mu over epsilon. That is what you have here. And that's called the impedance of free space, or the impedance of the wave impedance. And then this differentiation is what we did before. You saw E plus E minus JKZ minus E minus E JKZ. And this impedance in free space, if you use free space, then this is equal to square root of mu naught over epsilon naught. And this becomes equals what? 377 ohms. So the impedance of free space is 377 ohms. So now, you have it. This is how the plane wave propagates. So you have two components, the E component and the H component, and they are at right angles to each other, all traveling in a particular direction. So say you have EX, HY, sorry, EX, HY, and they're all traveling in the what? Z direction. So they are called transverse electromagnetic wave because they are perpendicular to each other. The red are the E and the blue are the H. You can see from this diagram that they are perpendicular to each other. The fact that the E and the M are perpendicular to each other is what is called transverse electromagnetic wave. And again, this brings us to the introduction or to of the second part of the Maxwell's equation and the time-varying electromagnetic fields and Maxwell's equations. So we have pretty much gone through everything. If there are any questions, we can ask. And please, even after now, while you're doing the assignment, if you have any question, you can either send me you should send me an email. I'll try and reply to your question via email. If there are any illustrations, I'll do that, and I'll send you the answers. And for now, if there are any questions, please, we can ask them, and then we can wrap up this